Good day, dear colleagues. For your attention, we present a report on the topic development of a microcontroller-based climate control system using neural network technologies. Modern climate control automation increasingly relies on artificial intelligence and neural networks. An optimal indoor microclimate boosts comfort, employee productivity, and equipment longevity, which is vital for business. Traditional systems regulate temperature and humidity mechanically or programmatically, but modern adaptive systems use real-time data and machine learning to predict and adjust climate conditions based on environmental changes and user preferences. The growing demand for energy efficiency and comfort drives the development of intelligent systems. Neural networks enable smart systems that adapt to internal and external conditions, integrated with IoT devices to optimize energy use. These innovations reduce maintenance costs and align with smart city goals by lowering carbon emissions and improving resource efficiency. In recent years, automated climate control has gained significant attention due to advances in microcontroller technology and artificial intelligence. Neural networks enable adaptive systems that optimize microclimate parameters based on environmental changes and user needs. Current research focuses on three main areas: classical control algorithms, fuzzy logic, and neural networks. PID controls offer stability but lack adaptability. Fuzzy logic considers user behavior but requires precise rule configuration. Neural networks are increasingly used in climate systems. CNNs analyze historical data to predict changes with LCTM as handle dynamic adjustments. A promising direction is integrating deep learning with IoT for distributed monitoring and adaptive control. Oral classical approaches are being replaced by intelligent methods. Future development lies in improving machine learning algorithms and integrating neural networks into microcontroller-based platforms. The analysis of current climate control solutions highlights two main approaches. It's traditional system using classical regulation algorithms and modern system based on machine learning and neural networks. Traditional systems typically using PID controllers maintain environmental stability but lack adaptability to changing conditions. They are mainly applied in industrial and commercial settings where stable parameters are essential. In contrast, AI-based systems, especially those using neural networks, offer adaptive climate regulations. These systems can analyze historical data, predict changes, and adjust operations in real time, demonstrating greater efficiency and flexibility in dynamic environments. Among the leading climate control solutions, several notable systems stand out for their use of AI and smart technologies. This study aims to develop a microcontroller-based climate control system using neural networks technologies. The goal is to create an intelligent system for automated monitoring, analysis, and adaptive regulation of climate parameters to maintain, conform, and maximize energy efficiency. To achieve this, existing approaches, classical regulators, fuzzy logic and neural networks will be analyzed for their strengths and limitations. Maintaining comfortable microclimatic control conditions is a constant human need. while the brain naturally processes temperature, humidity, and airflow to make adjustment. Modern systems automate this using microcontrollers and neural networks. Implementing such a system involves several key stages. Uh, Initialization, setting up the microcontroller sensor interfaces and communication modules, data collection, gathering and initially processing sensor readings, temperature, humidity, airflow, data transmission. It's sending data via communication modules for further analysis. Neural network processing, determining thermal comfort levels from the collected data, decision making, and last one is adaptation. The neural network refines its parameters to enhance control algorithms over time. One of the key stages in system development is the application of an object-oriented approach, which allows logical structuring and the entire system into unified modules. The use of case diagram shows in Figure 1 illustrated the relationships between actors and use cases. An office worker can input personal climate parameters and monitor the current microclimate status. The administrator has additional capabilities, including configuring the neural network, adjusting system parameters, and remotely monitoring its status. The sensor system is responsible for collecting the data necessary for making management decisions. The class diagram illustrates the system structure at the class level, including their attributes, methods, and relationships. In the case of this system, the sequence diagram shows how sensors data is transmitted to the microcontroller, where it's processed by the neural network. The results are compared with the expected values, and based on the comparison outcome, a control signal is generated to adjust the climate control devices. So this allows for a precise identification of when and how the system's operation will be corrected. A central element of the climate control system is a neural network trained using the error backpropagation algorithm. This approach ensures accurate regulation by minimizing prediction error while keeping computational demands allow, making it suitable for microcontrollers. An effective method for predictive climate control is an error predictive controller (NPC), which forecasts system states using neural network-based empirical models. This approach considers the interconnections between microclimate parameters, enabling adaptive system adjustment and optimizing control action with allowed limits. The next step was modeling the main stages of the system operation using an algorithmic apparatus. As a result of using the properties of the algorithm, so we subtract the common unit terms by the sign of the elimination operation and obtain the following formula of the algorithm. According to the presented model, the first stage is the initialization of the system, which includes setting the clock frequency of the 80 MHz microcontroller to 8 MHz, configuring the timers for processing delays and interrupts, setting up the I2C interface for communication with the sensors, and initializing QSR for communication with the GSM module. In the lab center electronic Proteus environment, a data monitoring subsystem was developed featuring a 5-volt transformer power supply and Mega32 microcontroller and CH221 sensor and CM900D GSM module. An LCD display shows measurement results, while LED is indicate the threshold branches, green for humidity, red for temperature. Simulation of this system provides data of training a neural network. The result of the network training is shown in this slide. To implement the repeatability of the system, it's necessary to modify the optimal values, which is done through the system performance assessments by office workers. As seen on the graphs, the desired error value of 10 in first power was achieved after 1149 iterations. The training, testing, and validation graphs are shown in slide. To verify the system is functionally, we will run the created model and display the graphs of the measured and controlled parameters as well as the PMI index. And this research resulted in the development of a microcontroller-based climate control system utilizing neural network technologies. Traditional methods like PID controls were found limited in adapting the dynamic conditions, while neural networks significantly enhance system efficiency. The system automates monitoring and adaptive regulation of temperature, humidity, and airflow prediction climate changes to adjust device operation. Using the PMI index improved control algorithm optimization, UML diagram facilitate clear system design and component interaction. The prototype testing in MATLAB demonstrates effective maintenance of the comfortable microclimate conditions with the minimum energy use. Future work will focus on advancing machine learning algorithms, enhancing adaptive control, integrating IoT technologies, and improving climate prediction accuracy through deep neural networks to further optimize the system. Thank you for your attention.